Okay, so we've got a 22-minute project and the timeline is across the top of the board here. And we've got a network diagram for the project here. We're going to work out the earliest start times and the latest start times. We're going to work out float times for the activities and determine the critical path. So the first thing to note is that before I can happen, if we come along here, F is an immediate predecessor for I, and D is an immediate predecessor for F, and C is an immediate predecessor for D. So C, D, F, I is one chain of activities that must happen in that order during this project. I've lined up C, D, F, and I along the board here, and as you can see, it takes 22 minutes. Now, in that time, we also have activity A, which takes 8 minutes. It's only a predecessor for activity E, and activity E has to start before activity I, and that's the only activity that activity E has to finish before. So activity E can happen anywhere in this time, as long as it happens before activity I and after activity A. So activity E can actually start at the 14-minute mark, as you can see, and still not delay the project because activity I can still have its full 2 minutes to run its course. If activity E started any later, it would push I further forward, and now the project would take longer than 22 minutes. So we'll bring activity E back to the 14-minute mark because activity E is a predecessor for activity I. Activity A can start any time in this range here because activity A only goes before activity E. So activity A could start at 0 minutes if you wanted it to, or it could actually start its latest start time. So it ends up there, would be at the 6-minute mark, which gives a float time of 6 minutes. Goes from 0 up to 6, where it can be. Activity B is a predecessor for activity E. There's a dummy activity in here, but activity B actually goes right before activity E. So all that's got to happen is that B has to happen before E. So B could happen anytime along there. So the earliest that B could start would be at 0. And the latest start time for B would be up there at the 12-minute mark. As I said all before, these activities are all in one big long chain. F has to happen before I, and D has to happen before F, and C has to happen before D. But here's an activity here, activity G. Activity G has to happen after C. So we finish C and G begins. But G is an immediate predecessor for H. So G could happen at any time in that range there. And H could happen any time in that range of times there. So there's a bit of float time for activities A, B, E, G, and H, but these others need to happen all in a row without any waste of time in order for the project to finish in the minimum time. So let's forward scan and backward scan to find the earliest start times and the latest start times, and then we'll find the float times and the critical path. So if we start here, activity A, B, and C can all start at the 0-minute mark if they want to. So that's the earliest start time that they can have, as you can see from the diagram. Now, activity A takes 8 minutes, so activity E has to wait until activity A happens. So it's going to have to start at the earliest 8 minutes later. If activity B happens, it can happen anywhere in this range, but activity E has to wait for activity A. So the earliest activity E can start is at the 8-minute mark. Well, what about the earliest that activity D can start? Activity D has to wait for activity C. So it's going to have to wait 5 minutes. You can see that there, 5 minutes, and then activity D can start. Activity F had to wait for both C and D, which was 5 and 5. So activity F, 5 plus 5 is 10. And then activity I has to wait for activity F, which is another 10 minutes. So activity I is going to have to wait for 20 minutes before it can begin. And then we have 2 more minutes. And the project is finished. Activity H down here has to wait for activity G to finish. The earliest that activity H could start is at the 6-minute mark. 5 minutes for C, 1 minute for G. H could start there at the 6-minute mark. The earliest that G can start is at the 5-minute mark. So they're the earliest starting times. Now we're going to work from the back end of the diagram here, the finish, that way to find out what the latest starting times are. So 2-minute activity, the latest that I can start and still finish the project without delaying it is at the 20-minute mark. So we put a 20 in there. That makes sense at the 20-minute mark. The latest that F can start without delaying anything is at the 10-minute mark. 20 minus 10 is 10. The latest that D can start without delaying anything is at the 5-minute mark. 10 minus 5 is 5. And the latest that C can start is at 0, because none of these activities can afford to wait, because they all, there's no float time, there's no sliding that can happen at all between them. If we go along this route here, 20 take off 6 is 14, which is saying the latest E can start is at 14, 20 minus 6. Up here you can see that E can start at 14 and still not delay the project. That's when it starts to push on the activity I. What about the latest that A can start? Well, as you can see here, if E is pushed all the way forward that it can be, A can actually start at the 6-minute mark. 14 minus 8 is 6. What about B? Well, the latest B can start is all the way up there, because B is a predecessor for E. So the latest that B can start, 14 minus 2 is 12, and you can see that there, it can start at the 12-minute mark. The latest that H can start, 20 minus 4 is 16. Let's see that work out in practice. The latest that H can start here is in line with 16. And the latest that G can start, 16 minus 1 is 15. And we check that out there. The latest that we can do G is at the 15-minute mark, as we see there. So we filled in these little boxes here. The first thing in each box, the first number is the earliest start time, and the second number is the latest start time. And any of the boxes that have the same numbers in them are lying on our critical path because there is no float time. For example, this one here has a 20 and a 20. That means that I lies on the critical path. F has a 10 and a 10. They're the same. There's no float time. F lies on the critical path, which is this one here. And you see all these ones on this chain of activities lie on the critical path, and they also have digits that repeat. So you can tell which ones lie on the critical path of the diagram of the network. And you can also write the critical path down here because C, D, F, and I are critical activities. But the other activities have float times. For example, A doesn't need to start, it can start at 0, but it doesn't need to start until the 6-minute mark. So it's got 6 minutes of float time. Now you could also work that out by subtracting the latest start time, take off the earliest start time. 6 take off 0 is 6. So A has a float time of 6 minutes or whatever. What about B? Well, B can float anywhere in this from 0 all the way up to the 12-minute mark before it begins. Or if you like, 12 minus 0 is 12. So B has a float time of 12. As we said before, C has a float time of 0 and it's a critical activity. G, we're saying here, 15 minus 5 is 10. So G should have a float time of 10. Let's see how that works out in practice. G could start here at its earliest start time at 5 or all the way up here at 15, in line with 15. So that makes sense. It's got a float time in here of 10 units between 5 and 15. 15 minus 5 is 10. So G has a float time of 10. H has a float time of 10 as well. And we can see that because H could, at its earliest, start here at 6 and at its latest, start in line with 16. 16 minus 6 is 10. So H's float time is also 10. And all the other activities, C, D, F, and I, have float times of 0 because they are critical activities and they make up the critical path. The critical path is going to determine the minimum time the project will take. And the minimum time this project took is 22 minutes because that's the sum of all the times that the critical activities take.